on the recording button. So we're going to record now. Sorry, we forgot that. So I share my screen. So here we go. So let's start off by drawing the circuit. So what we have is our initial qubit, which is in a totally arbitrary state, alpha ket 0 plus beta ket 1. And then we input two additional qubits, which play the role of ancillary qubits, and they happen to be in a Bell state, which is 1 over under root 2, 0, 0, plus 1, 1. And then we do the following operation. We have a controlled NOT gate acting on the second qubit. This is followed by a Hadamard gate on the first qubit. The third qubit, by the way, goes to Bob, so it goes far away. And what we would like to do, all of this part of the system belongs to Alice. So what we could do, we could look at the quantum state over here. We could look at the quantum state over here. And we could all look at the quantum state over here. So let's call this quantum state psi 3. Let's call this quantum state psi 2. And let's call the input quantum state psi 1. Now, if you observe here, we are using an entangled state. So entanglement here is being used as a resource. All right, so our initial state is psi 1, which is simply alpha 0, 0, 0 plus beta 1, 1, 1, with, of course, an under root 2 with it as well. Okay, so there is no problem with this initial state. And as you saw in Sajda's calculation, once the control NOT is applied, so the control NOT is applied on the second qubit with the first qubit as the control qubit, so the target is the second qubit, the state psi 2 becomes the following: 1 over under root 2. Nothing happens to the coefficient alpha. Here the first qubit is 0, so nothing happens to the second qubit, 0, 0, 0, plus beta. The first qubit remains unchanged. The second qubit flips, 1 becomes 0, and the third qubit is preserved. So this is what we observe at stage psi 2. And then we put a Hadamard gate on just the first qubit. So all of this is happening at Alice's end. Remember that the entangled state has been prepared in prior. It's already been prepared. And one of the qubits in the entangled state has been given to Alice, and the other qubit has been given to Bob. So the Hadamard gate now acts on the first qubit. Okay, so let's do that. Psi 3 becomes 1 over under root 2. Alpha just remains alpha. The first qubit now changes its identity. It is transformed, in other words, it becomes 0 plus 1 over under root 2. So I put under root 2 outside here.
مين بده يفطر انت ومين؟
So alpha, 0 becomes 0 plus 1. And the second and third qubits remain unchanged, plus beta. And then what I would like to do, the first qubit is 1. So this becomes 0 minus 1. And the second and third qubits remain unchanged, as they should. because the Hadamard
Sorry,
gate
sir.
is a local quantum gate.
Sorry, sir. Could you repeat the last step?
All right, so what does a Hadamard gate do? The Hadamard gate takes 0 and converts it to a superposition 0 plus 1. Okay, this is the definition of a Hadamard gate. Likewise, the Hadamard gate takes okay. So is this clear, my friend? Can you hear me?
Sorry, I
Yes,
have very bad connection.
but the screen isn't shown.
Oh,
I
okay,
cannot
just a
see the
minute.
screen.
Just a minute. All right, so can you see the screen now?
Yes.
So what I've done is I've taken cat1 here and I've converted to 0 minus 1. I've taken cat 0 and converted it to 0 plus 1. So this is the action of the Hadamard gate on the first qubit. All right, my friend.
Yes.
Okay, so coming back to the state psi 3, what I would like to do now, I just write 1 over 2. I multiply the two square roots and I would like to expand this expression once again. So alpha 0, 0, 0 plus alpha 1, 0, 0 plus beta 0, 0, 1 minus beta 1, 0, 1. All right. Okay, so this is the state at this point here, psi 3. Now what Alice does is that she measures her qubits. Okay, so she measures the first qubit and the second qubit, and these are the only two qubits in her possession. So she can't do anything with the third qubit because Bob has walked away and possibly gone to a different country or a different city or a different continent or even a different planet and gone out into space, gone out onto a satellite. So Bob is gone. He's taken his qubit and is gone. And Alice only has the first two qubits with her, the original qubit that she wants to teleport the state of, and one of the entangled pair. So she takes her qubits, and after these operations are done, she measures the states of her qubits and projects each one of them into the cat 0, cat 1 basis. So, as you know, we've labeled our state measurement devices in the following fashion, and we've modeled them through these beam splitters, polarizing beam splitters. So we have four outputs, P0, P1, another P0, sorry, and another P1. Okay, so these are four possible outputs. And if I were to write the possible outputs that Alice sees, she could see 0, 0, or she could see 0, 1, or she could see 1, 0, or 1, 1. This is her first qubit, whereas the latter is her second qubit. For example, if this detector clicks and this detector clicks, she would have declared that her output is 0, 0. If this detector clicks, this one and this one, then she will declare that her output is 0, 1, and so on. So she gets four possibilities of 2-bit strings. So she started off with quantum states, but now she has a measurement and her outputs are bits. They're not qubits, they are measurement outcomes, zeros and ones. Okay, so this is a set of classical information. There are four possibilities: possibility 1, possibility 2, possibility 3, and possibility 4. And there is going to be a probability for each one of them. So let's find out find out these probabilities. So what the clever thing that I could do now is I could rewrite the state psi 3 in the following fashion. If you observe, so if I were to take this state and this state, so have I made some error here? Can you? Uh,
I think in the first psi, uh, we forgot to add alpha 011 plus beta 100, the cross terms.
which state? Psi 1?
Psi 1, yeah. It's 4 terms.
Oh, I'm so sorry about that. I'm so sorry about that. I'm really sorry about that. So let me let me repeat this calculation. So sorry. Thanks for pointing this out. Right. So my initial state psi 1. Let me change the color. Initial state psi 1 is the first qubit is in an arbitrary state alpha z cat 0 plus beta cat 1, and the second and third qubits are in the entangled state 0, 0 plus 1, 1. So I can expand this as 1 over under root 2 alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 0, 0 plus beta 1, 1, 1. Okay. Now I put a controlled knot on the second qubit controlled by the first qubit, and my state becomes psi 2. So let's work it out. 1 over under root 2 alpha 0, 0, 0 plus alpha 0, 1, 1 plus beta 1, 1, 0 plus beta 1, 0, 1. Is this making sense now?
Yeah.
Okay. And then I would like to do a Hadamard gate only on the first qubit, and I would get psi 3. So I just put 1 over 2 because 1 over under 2 factor, an additional square root 2 factor comes from the Hadamard gate. Then I have alpha. Instead of ket 0, I need to write a superposition. So this becomes 0 plus 1. This means 0, 0 plus alpha. So I go step by step. This 0 again transforms to 0 plus 1. Ket 1, 1 plus beta. This ket 1 here becomes 0 minus 1. The other two qubits remain preserved, plus beta. So I just expand all of this algebraically as follows.
Excuse me, sir, could you recheck your internet? I think your screen has been stuck and you're also not audible. Kindly wait while he tries to reconnect.
Sorry, my internet got disconnected. Uh, my video is not working at the moment, so but we'll figure out the video in a while. So can you hear me?
Yes, sir, we can. And we can also see your screen now.
All right. So I'm sorry about that. My internet got disconnected. So this is the state psi 3. So what psi 3 at this stage, Alice measures her 2 qubits. So in order to look at the outcomes, let's rewrite the state in a slightly different fashion. So let's look at the terms in which the first 2 qubits are 0, 0. So I have this term and I have this term here. So what I could do, I could play the reverse simplification and factorize out the first and the second qubits, which are 0, 0. And the third qubit, I could write this as alpha ket 0 plus beta ket 1. Okay. So the two terms that I've put tick marks on top of it, black tick marks, I've just rewritten those two terms in the fashion that appears on the screen. And then what I could do, I could take, I could now take the terms in which the first 2 qubits are in a state 0, 1. So uh, that would be this term here, followed by this term here. So I could do a similar factorization and write it as these two terms as ket 0, 1 followed by alpha ket 1 plus beta ket 0. Okay. Now let's take two terms in which the first 2 qubits are 1 and 0. So here I go with this term and I go with this term over here. So if I were to write these two terms together, I would write ket 1, 0 for the first 2 qubits, and for the third qubit I could write alpha ket 0 minus beta ket 1. And now two terms remain, and for those two terms I have the first 2 qubits in the state 1 and 1, and finally I would write alpha ket 1 minus beta ket 0 for the third qubit. Now I hope you already know what's happening here. So for convenience, I'm going to redraw the circuit in a slightly smaller size. So I have a controlled NOT gate on the first two qubits, followed by a Hadamard gate on the first qubit. And here I do a measurement, some kind of measurement. Alice does a measurement. And she gets four possibilities. So let me write those possibilities like this. She gets 0, 0, or 0, 1, or 1, 0, or 1, 1. And the third qubit belongs to a different party. This belongs to Bob. This is going to Bob. This is what is happening in Alice's realm. In Alice's world, she gets a measurement and gets one of these four outputs which I've written in green. The first output 0, 0 corresponds to this measurement here. The second output 0, 1, this one corresponds to this measurement. The third output corresponds to this measurement. And the fourth output corresponds to this measurement. All right. Now, what is the probability of each output?
The modulo
Can
square for each amplitude.
Sorry, can you say it again, please? 1 over
Um,
4. Yeah, it's 1 half squared. Each of these terms comes with 1 half, right? So the probability that the first two qubits are projected in ket 0, 0 is going to be the square of this term, 1 half. So each one of these probabilities, the probability 0, 0 is the same as the probability 0, 1, is the same as probability 1, 0, is the same as probability 1, 1, and this is equal to 1 half squared, which is 1 quarter, 25%. So Alice gets one of the four possible outcomes with equal probability. And it's a totally random result that she gets in one go. She performs her experiment in one go. She'll get either of these four outcomes with exactly a 25% probability. So it's like tossing a coin with four faces, or tossing two coins which are totally fair. Now what she does is she writes her output. She writes her output on a piece of paper. So she can get four outputs. Suppose she gets the third output, 1, 0. She writes her output on a piece of paper, scribbles it, and sends the results to Bob over a classical channel, which means she makes a phone call, or she uses the satellite, or something that is limited by the speed of light. All information, all signals, by virtue of special relativity, have an upper limit on the speed, and that limit is the speed of light. So she sends this classical information over a classical channel to Bob. Now, Bob doesn't know what his qubit is going to be. His qubit is totally unknown to him. And it turns out that his qubit could be in either one of the four possibilities, which I'm underlining in green. It could be alpha ket 0 plus beta ket 1. It could be alpha ket 1, beta ket 0, alpha ket 0 minus beta ket 1, or alpha ket 1 minus beta ket 0. And he's totally ignorant of what his qubit is going to be. And he cannot measure the state of the qubit. He cannot perform an experiment and tell what his qubit is going to be. If he tries to do that, he's going to destroy his qubit. So what Bob does is that if he receives information from Alice, dependent on the information he receives, Alice and Bob have already decided that they would like to implement some transformation on Bob's qubit, so that the original state psi, which is the state of the first qubit, which is alpha ket 0 plus beta ket 1, is recovered over here. So the goal is to recover or teleport the original quantum state alpha ket 0 plus beta ket 1 at Bob's end. All right. So if you look at the state psi 3 that I've written over here, can anyone tell me what's going to happen if Alice's message is 0, 0? What should Bob do to his qubit?
Nothing.
Nothing. Bob should do nothing. This means that Bob should implement a unitary gate, which is just the identity. Nothing. So he will be extremely happy that he doesn't even have to expend any energy. He doesn't even have to roll up his sleeves and do a transformation. His qubit is automatically a copy of the original qubit. Quantum mechanics ensures that. Okay. If Alice's message, on the other hand, is 0, 1, let's see what Bob's qubit is. Bob's qubit is now given by what I'm circling in or highlighting here. This is Bob's qubit. Now, what should Bob do to his qubit without measuring it so that he ensures that his qubit is a copy of the original qubit at Alice's end?
Not gate.
Not gate,
Mm.
exactly. In that case, Bob should do a not gate on his qubit, on the third qubit, which is in Bob's possession, a not gate. And we all know that the matrix for a not gate is 0, 1, 1, 0. Okay. If likewise, if Alice's message received by Bob is 1, 0, let's look at what Bob's qubit is alpha ket 0 minus beta ket 1. What should Bob now do?
Pi, pi.
Sorry, Hadamard?
No, pi, not yet.
Pi gate, a phase gate with a phase pi, which is given by 1, 0, 0, minus 1. Okay, which converts ket 0 to itself and converts ket 1 to minus 1, ei pi 1, which is minus 1. Okay, and the last possibility, if Alice's message turns out to be 1, 1, Bob's of course reads this message. And if it turns out to be 1, 1, then what should Bob do to his qubit?
Not gate first, then a phase gate.
Yeah, or it doesn't matter. The order doesn't matter.
Yeah, it's the phase. There is
Okay.
a difference as a global phase, right?
Yes, exactly. So NOT gate followed by a phase gate. So if I would like to write the matrix for this, a NOT gate is 0, 1, 1, 0, and a phase gate is 0, oh, sorry, 1, 0, 0, minus 1. So I can perform this multiplication. I will get a 0 here. I'll get a 1 here. I'll get a minus 1 here. And by the way, these four gates are really important. These four kinds of matrices are important. This is just the identity. In physics, this gate over here is generally written as sigma x, sigma with an x, and this gate here is
Sigma
written
Z.
as sigma z, and this gate here is sigma, so sigma y is 0 minus iota, iota 0. If I write I sigma y, this is 0 minus 1, 1, 0. Minus iota sigma y, this becomes 0, 1, minus 1, 0. So this thing over here is minus iota sigma y. So it's proportional to the sigma y gate. So these are just fancy names given to these gates. And in physics, if you study physics, these are called Pauli matrices. So Bob has to apply a Pauli transformation on his qubit to recover the original qubit. So I have one question, and in the meantime, I'll try to turn on my video as well. The question that I would like to ask is no cloning violated here?
No.
No.
All right. So can anyone just tell me why? Why is
Uh,
no cloning not violated?
because Pauli doesn't cloning the Alice's state. He just take the result and do a process on it.
No, but
I guess
Can I?
because the qubit was recreated from scratch.
No, the state, the Alice state had been destroyed because of the process that we have done for it and the act of the measurement. So the first state that we already have, the Alice one, was destroyed. So the Bob one is not the same as the Alice one.
exactly. So was this Sana?
Yeah.
Yes. So you're perfectly right. Whosoever has answered this question, they're perfectly right. In the process of teleportation, what we've done is, if you observe here, let me go back to the original diagram that I've made. Here, what's happening here? A measurement is being made, and the first qubit, whose information is being transferred from Alice to Bob, is being destroyed. The measurements that are done at Alice's end, they are demolitive measurements. They demolish the state. They destroy the state, because then the photons are gone, or then the particles don't exist any longer, because they have impinged on the detector, converted all their energy and given it to the detector, converted into sound energy, or the click or the movement of a needle. All the energy is gone, the particle has been destroyed. However, by the classical information that is received, which is a result of the measurement outcomes, Bob does a quantum operation on his qubit, and lo and behold, he recovers the original state. So, in the process of transfer of information, teleportation is really the transfer of information from Alice's end to Bob's end. And in the process, no cloning is not violated, because the original qubit or the particle is destroyed in the first place. And this scheme also does not violate special relativity. So it's not that Bob's qubit is automatically superluminally in no time a copy of Alice's original qubit, because time is required, finite amount of time is required for information to travel classically from Alice to Bob. And if Bob does not receive any information, he's totally ignorant of the state. His okay, if I ask you the question, if Bob does not receive any information from Alice, what is the identity of Bob's qubit? So I hope you get my question. My question is, if Bob does not receive any information from Alice, what is Bob's qubit? What is the state of Bob's qubit?
Bell state.
Del state? No, Bob has just one qubit. So
It's
it can't be the del.
superposition.
It's
Superposition between four probabilities.
uh, yeah. So what the correct answer to this question is that this is not a valid question at all. So this is a strange answer, that the question that I'm asked is not valid quantum mechanically. Bob Bob's state is a totally mixed state. It's a random state. So in the meantime, let me try to restart my camera. Just a minute, please. Okay, so it's just a minute. Here you go. It's always nice to see what's going on. Okay, so start video. Bob's state is totally unknown. It's a mixed state. It's not even a pure state, and you can't say it's a superposition. For example, look at a simple example. If I have an entangled state, a Bell state, which I say right over here, phi plus, which is 1 over under root 2, 0, 0 plus 1, 1. So this state phi plus is fed into some system. One of the qubit goes to Alice, and the other qubit goes to Bob. And Bob does a measurement on his qubit. And there are two possible outcomes, cat 0, cat 1. This is the probability P0 and this is the probability P1. And furthermore, suppose there is an opaque wall between Alice and Bob, which means no transfer of information is allowed from Alice to Bob and vice versa. No classical information can travel in between. Bob lives in a different world altogether and has no clue that Alice even exists. For him, Alice is no one. So now Bob does a measurement on his qubit. What is the probability P0 and what is the probability P1?
Half.
What are these?
1/2.
Each one of them is 1/2. Okay. Now this means that the outcome is totally random. And Bob knows nothing about his qubit. Before he makes a measurement, the Bob's qubit is not in a superposition. It could be anything. For example, there are if Bob's qubit were, suppose the two states were separable. Bob's qubit could be cat 0 plus 1. It could be cat 0 minus 1 over under root 2. It could be cat 0 plus ei pi by 3, 1 over under root 2. All of these different possible states will give the same probability outcomes. The statistical outcomes of the experiments that Bob will perform could could come out of a variety, in fact, an infinite variety of possibilities. So Bob's qubit, unless he makes a measurement and unless he receives from some information from Alice about her qubit, is a totally random state. We call it a totally or a maximally mixed state. And we cannot represent the state of Bob by a vector or a ket. It can only be represented by what is called a density matrix and a maximally mixed density matrix. So I cannot say that Bob's qubit in the teleportation example is a superposition. It's a mixed state. It's a totally random state. And uh, and, and I haven't discussed mixed matrices or density matrices in this course, but things get really strange when we look at subsets of entangled states. By the way, one important property of entangled states is the following. Suppose I input, okay, there seems to be a question. Yes, Madiha, please ask the question.
Assalamu alaikum. I have this tight question. You said that the Bob's in the teleportation example, the Bob's bit is totally random. So can we say if we
Qubit.
can go a little bit up, the 4 qubit combinations we got, can we say that these 4 combinations exist at the same time at the Bob's end? Can we say that the 4 qubits, psi 3? Yes, exactly. The- The
So by
third
the way,
qubit,
these are three qubits.
uh, the four combinations,
So
0, 1, alpha 0, beta
the
plus
fourth
beta 1.
here, you can look at this thing here.
Yes. The next step, in which you have four qubits with red,
So,
orange, purple, and black.
so Madiha, these are not four qubits. These are three qubits, and any three qubit state can be written as a superposition. So this is a superposition of three qubits. Okay, and there turns out to be 8 terms in the superposition, and there is a coefficient, a probability amplitude, either alpha or beta, with a factor of half with each term. So this is not, these are not four qubits, these are three qubits, and we have a superposition.
Yes, but the third qubit is being teleported to Bob. So Bob is actually receiving only one qubit.
Is the internet connection interrupt?
So this is my discussion on quantum teleportation. What was I meant? I was talking about. Can you remind me where we left off?
I think you were having a discussion with Madiha, and then Rana Imran also had a question.
All right. So I don't recall Madiha.
Madiha, if you could just take us
Yes,
from where you left.
I had a slight confusion about what Bob is actually getting. Bob is getting one qubit, if I'm right. So I know that the final result psi 3 is actually the superposition of three qubits, but
Mhm.
and the Bob's qubit is random. But can we, mathematically write that down? That
Yes,
that
we
that
can.
thing that
We can.
Bob is getting.
Yes. So, Madiha, can I ask you what is your background?
I am electrical. I'm from electrical engineering,
All right.
but these days I'm working on information security and special focus on quantum computing for that.
All right. So what we could do mathematically, that will help me answer your question. So what we could do is, if I have a two qubit state, phi plus, and Alice state, I just don't care about Alice's state. So I put it in a dustbin. Now the question is that if this initial state is an entangled state, a Bell state, a maximally entangled state, sorry, 0, 0 plus beta, so sorry, 0, 0 plus 1, 1, and the first qubit is totally ignored, then what is Alice's qubit? Okay, so this is the question. What is Bob's qubit? Because
Yes,
Alice's,
what's Bob's qubit?
what is
Yes.
Bob's qubit? So the answer to this question is that Bob's qubit cannot be represented by a pure state. It is a density matrix, rho, which is equal to the identity matrix, which is 1 with the factor of half, 1, half, 0, 0, half. Now, what is a density matrix? A density matrix is the most general way of writing a quantum state. We've seen that quantum states have been written as ket psi, but this is not the general form. Suppose I have a box and I have two particles in the box. One is a black box, or a black particle, and the other is a red particle. Now this
Mhm.
box is closed. It's in a closed environment and I can't see inside. So it's in a black box. It's opaque. Now there's an observer outside. Suppose these are quantum particles as well. Now if the observer breaks open the box, right? The box is broken open, it's gone, right? And the observer, while keeping his eyes closed, picks up one of the particles and brings it out. He doesn't know beforehand which particle has he picked. Suppose he just picks out one particle, returns out, and he opens it and opens his eyes and looks at the particle. Suppose it's red. Well, that's good. He could put the particle back in and then shake the box again, and then perform another experiment. So what the observer is doing is that he's making a measurement,
Yes.
and he's taking some results which are a posteriori. After the measurement, he's observing whether he gets a red particle or a black particle. But what
True.
is the state of the box, or this combination of particles before he's made a measurement? That's the question. In quantum
Yes.
mechanics, you cannot write this as red plus black. Okay? What in quantum mechanics, what you would do is you would write the state of this box as ket red, bra red plus ket black and bra black over under root 2. Now this is not a ket of, because there are bras involved. This is called a density matrix. So this state that I've written on the red is a coherent mixture. Okay. Whereas the state that I've written on the left is an incoherent mixture. If I have ket psi and ket phi, and both of them are pure quantum states like the ones that we've been dealing with, then I can make a superposition of these states. But then what I would have to do is I need to put in a coefficient here and a coefficient here, C2. And this gives me a new pure quantum state. But there's a constraint on these coefficients, and that constraint is that C1 plus square plus C2 mod square must equal 1. So the example of a state that I've written here is a pure quantum state. Okay. However, if I have a mixture of states of this kind, so if I represent this is the red quantum state, and if this is the black quantum state, I could express the incoherent mixture as ket psi bra psi and ket phi bra phi, and I need to put in some coefficients here, P1 and P2. And these P1s and P2s are not probability amplitudes, rather they are now probabilities. And P1 plus P2 must equal 1. Okay. So,
Okay. Thank
so
you. That's a different. That's
yeah,
a different concept, and
right.
okay.
So
Thank you so much.
it's very hard to say unless you are dealing with density matrices. It's hard to say what the state of uh, Bob's qubit is. Bob's qubit, in other words, is perfectly, it's totally mixed. In other words, there is complete lack of information about Bob's qubit, and unless one does a measurement, you can't say what the state. It is a random mixture, an incoherent mixture of states. Okay.
And
Uh,
actually, that's the property that helps in encryption and everything because it's completely random state.
exactly. So the next lecture, when I talk about quantum communication, I'll give examples of this. A maximally entangled system is a system that if you look at one subspace of it, it turns out to be totally random. The reduced density matrix of a maximally entangled state is maximally separable. It's maximally mixed. That's how we define maximality of entanglement. So if you have an entangled system and it's the beauty of it is that if you just looked at one subsystem of the bigger system, it turns out to be totally random. Like the example that we've seen over here. The input state is pure here. It's maximally entangled. It's a pure state. It can be written in this form. However, if I just look at Bob's qubit, the outcomes are totally random. But if Alice and Bob both were to make measurements and they would compare their notes after the measurements have been made, they will observe that their outcomes are totally in sync with one another. So this is the strange and eerie and weird thing about quantum mechanics and about entangled states. That is, the sum is uh, the sum turns out to be correlated, but the whole is correlated, but the components of the whole, they when looked alone, they are perfectly random.
Thank you so much. Thank you so much for such an elaborate answer. Thank you so much.
So I can take more questions, and I can give another homework for the next before the next class.
Okay, I want to add something and then probably ask something as well. Can we, because I think if you look at this discussion from the point of view of the spin state of an electron or any other quantum particle, it's just like saying if you have two entangled particles, correct me if I'm wrong, you know, if that's what I understand. If you have two entangled quantum particles in terms of their spins, their spin up and down, of course, the spin could be in either direction, that is X, Y, or Z. But as long as you do not detect, do not measure any of those two entangled particles, they could be in any direction, X, Y, or Z. Once you actually do measure one of the particles, and let's say if it's in the X direction, if you measure it to be in the positive X direction, then the other particle, the entangled particle, would be in the negative X direction. That is exactly opposite to it. But as long as you do not measure those particles or any one of the particle, it could be in either X, Y, or Z directions. Is that something related to what we are discussing right now?
Mujtaba, can you hear me?
Yes, sir.
Mujtaba, definitely. If you don't measure the particle, it's totally random. It could be in a mixed state, and you can't say whether it's in X, Y, or Z direction. You don't know what the spin direction is in. When you perform a measurement, as far as spins are concerned, when you perform a measurement, uh, then the act of measuring the spin direction of an electron, say, it necessitates the definition of an axis.
Yes.
Okay. For example, if you want to find the direction, so let me draw an example here. This is an electron, okay, and it has some quantum state psi, which is the spin of the electron. Now, if you want to determine the spin of the electron, what would you do? You would give this electron some velocity and pass it through a device, which is called a Stern-Gerlach apparatus. Okay. What the Stern-Gerlach apparatus does is that it produces an inhomogeneous magnetic field. Okay, and as this particle with a spin comes out of the Stern-Gerlach apparatus, there are two possibilities. Either the particle can go up or it can go down. So this is just like the polarizing beam splitter, but now we're looking at the spin of an electron. Now you have defined an axis, which is the axis defined by this Stern-Gerlach, this inhomogeneous magnet pole pieces which are curved. So there's a direction to it. There's a magnetic field gradient along the z-axis. You call it the z-axis. Now what you're doing is you're projecting the spin onto the z-axis. So you're measuring mu z, the z component of the magnetic pole. So the very act of measurement defines a basis. Okay, and you need to know what the basis is. Here the basis is whether the spin is aligned along the plus z axis or it aligned along the minus z direction, and the axis is the z axis. So the act of measurement necessitates necessitates the definition of an axis. But the original quantum state, if you look at the original quantum state, if I represent up arrow by plus z and minus arrow by minus z, The original quantum state could be plus z, minus z, say plus minus z plus z. Okay. This state will give the same results as plus x minus x plus minus x plus x. Okay. And this experiment will yield the same result as plus y minus y plus minus y plus y. Okay. All three experiments will yield the same result. Okay. So I think I've answered your question is that we can't say beforehand if I get this measurement outcome that half of the times the particle turns out to be deflected positive direction and half of the time it turns out to be deflected in the negative direction. I cannot distinguish between these three possibilities because they are non-orthogonal input possibilities. The particle could be in any one of these states. In fact, it could be at any arbitrary direction theta.
Yes.
Okay.
Yeah,
So
I
I
get
hope
that.
I've answered your question and I hope I've understood your question.
Yeah, that's right. That's right. Yeah.
Now, what I would like to do, sorry, the internet connection was very flaky today for some reason. I don't know why. I would like to give another homework before the next class. And this,
Doctor, can I ask you a question before
yes,
that?
yes, please.
If for the two entangled electrons, I measure the spin on the z-axis on one of the entangled pair, and then I measure the spin on the x-axis of the other one. What would I get? They are and they are mutually exclusive, so I don't know.
Yeah,
يعني will yeah.
that's a very good question. In fact, the outcomes will not be correlated. So let's, I would, I would say let's do a homework for this. So if your input state is ket 0, 0 plus 1, 1, right? So suppose you prepare this Bell state. Okay. Now there are two possibilities. And I think you should do this as a homework. This is a really nice question and a really nice opportunity to try out something on your own. I have two beam splitters, one for Alice, one for Bob. And these beam splitters project onto ket 0, ket 1 basis. Okay, like the examples that we've already discussed. And I have this input state. I would like you to find the probability P00, P01, P10, and P11. You already know that this probability is going to be half, this probability is going to be 0, this probability is going to be 0, this probability is going to be half, right? Sarah, is this clear?
Yes, it is.
Now your question, let's come to your question. Your question is the following. So let me talk about Sarah's question. Sarah has asked this question, which I really like, that Alice has a beam splitter and Bob has another beam splitter. And the properties of these beam splitters are slightly different. Alice's beam splitter projects on the basis 0 and 1. Whereas, so this is Alice. Whereas Bob's beam splitter is a different kind of beam splitter. It's not a beam splitter that sorts out horizontal and vertically polarized photons. Rather, it has one channel which outputs on ket 0 plus 1 over under root 2, and the other channel is 0 minus 1 over under root 2. And in shorthand, let's write this as ket plus and this state as ket minus. Okay. Now, the two measurement bases on Alice's subspace and Bob's subspace, they are different. All right. So I think this was your question.
Yes.
Okay. So you can call this to be x. So in your question, you call this x. And this you could call minus x. Okay. So this is how I would recast your question. Now, what I would like you to do as a homework is the probability of finding 0 on Alice's qubit and plus on Bob's qubit, probability of 0 on Alice's qubit and minus on Bob's qubit, probability of 1 on Alice's qubit and plus on Bob's qubit, probability of 1 on Alice's qubit and minus on Bob's qubit. And you already know that how do you find probabilities? You take your state, phi plus in this case, and project onto the state that you would like to find the probability for. For example, for this particular probability, you would have to project onto ket 0 and you put it in bra form. So you need to find out this probability amplitude and then take the modulus square. So let me write out the first term for you. So this becomes 0 tensored with ket with bra plus, which is 1 over under root 2, bra 0 plus 1. Put all of this in a big bracket and find its inner product with 1 over under root 2, 0, 0 plus 1, 1. Okay. So you need to compute this probability amplitude and remember to connect the first qubit with the first qubit and the second qubits here with the second qubits. Okay. Because you need to take the inner product in the same Hilbert space. So you cannot take the inner product of a first qubit with the second qubit. Okay. So this is how I would like you to find out this probability amplitude and see if the results that you obtained are identical to these results or they're totally different. Is there any correlation between the outcomes of Alice and Bob? Okay, so both Alice and Bob, you will notice that if you would like to exploit entanglement, you have to measure them in the same basis. And this concept is really important when you want to do secure communication in the quantum realm. Okay, so have I answered your question? In fact, I've recast your question into another homework problem.
Yes.
Okay. So the thing that I would like you to work on in the next, before we move on to the next class, is a topic which is related to quantum error correction. So the idea of quantum error correction is, of course, when you start building a quantum computer, there are always errors. Errors always happen. So you need to, unless you are able to, unless you are able to correct for errors, you won't be able to do anything useful. Suppose I consider one error which is called a bit flip error. And a bit flip error is that 0 turns to 1 and 1 turns to 0 by some noise in the channel. So you need to have a mechanism of detecting errors. But the problem of measuring quantum states is that once you measure quantum states, you destroy them. They are no longer good to be used because you've disturbed them or you've destroyed them. So one possibility of doing error correction is the following. And let me pose this as a problem, and as a homework, I would like you to go through how the circuit that I'm going to develop or design on the blackboard or the whiteboard is going to help in error correction. Suppose I have a qubit 0, a physical qubit 0, and I encode this in terms of 3 qubits. I write this as 0, 0, 0. So the physical qubit is encoded into 3 logical qubits 0, 0, 0, and ket1 likewise is encoded as ket 1, 1, 1. All right. So this is reminiscent of the classical realm. If I want to transmit a bit 0, there's a probability that noise can flip this to 1. However, if I convert this to a string of zeros, say 5 zeros, then what noise could do is that noise could flip 1 bit to 1, but it's highly improbable that it flips 2 bits to 1, and it's even more less likely that it flips 3 bits to 1. So by encoding a single bit into more bits and then looking at whether majority of the bits are 1, I can do a majority voting. If majority of the bits are 0, I can presume that my original bit was also 0. And if the majority of the bits turn out to be 1, I can presume that the original bit was 1 and noise hasn't destroyed or changed the identity of the bit. A similar concept works here, even though I cannot clone quantum states. If I were to transmit qubit 0, I would use 3 qubits instead and initialize each one of them in the state ket 0. And I would, if I wanted to transmit ket 1, I would use okay. Now if I were to draw a circuit of the following form, so these are my 3 qubits, and initially my desired state was ket alpha plus ket plus beta ket 1, which I've now encoded as alpha 0, 0, 0 plus beta ket 1, 1. And if I transmit these qubits and use 2 ancillary qubits, which each one of them is initialized as ket 0, and I build a circuit of this kind, the question is, if only one bit flips are allowed, that is the original state that I'm putting in here, which goes in here, if only one of the bits is flipped, and this is a constraint on my circuit, can I look at the outcomes here and do a classical measurement on the outcomes here, and by looking at what outcomes I get on this, on these 2 qubits, which are converted into bits now, by looking at these qubits, can I tell which of the original bits has flipped and whether a bit flip has taken in place in the first place or not? So by looking at this classical information here, can I tell what kind of error has occurred on the 3 working qubits? And can I use that symptom or syndrome to correct the qubit which on which a bit flip has occurred? So I would like you to look at the state over here, with this being the ideal state. Then I would like you to look at the state over here, then the state over here, Likewise, the state over here, and then perform a measurement here and here, and check whether the measurement outcomes can be used as an identifier or as a syndrome for which bit has flipped on the first three qubits. And if we know that the second qubit has flipped, we'll of course flip it back again, do a NOT gate on the second qubit and flip it back again. So we have controlled NOT gates on the first qubit depending upon the classical information that we receive from the ancillary qubits. So can you see whether we can use this circuit to do quantum error correction? So this is the homework problem that I would like to finish off this lecture with, and we'll start with a discussion of this circuit in our next lecture, and we'll also look at non-locality and quantum communication. And the last lecture on the 8th day will be reserved for miscellaneous topics, some frontier topics in quantum computing. So I hope in these 6 lectures, I've tried to explain a little bit about how quantum computers work, what is quantum information, what are the special aspects of quantum information. It's hard to cover up all the material in 6 or 8 or 7 lectures. So I'll try to just pick up the major ideas, and I hope these can prove to be useful if you would like to foray into this area. So I'll be happy to take one or two last questions before we finish off the lectures for this week.
I have a question, please.
Yes, please.
In the previous lecture, when we do the inner product to have a probability, P00 give us half, and P01 give us 0. But when I repeat it in at home, I don't find the same result. I have half, 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 half for the 4, but is violate the normalization. I don't
Uh,
know.
yes. So is it possible for you to email the problem to me so that I can look at it and see what's going on?
Write my work and send it
Yes.
by email.
Yeah, because unless I see what you've done, it's hard for me to tell or put it on the Google Classroom. And if you want, this is my email address here. So for normalization, remember just one, if I have say a 4 qubit state, okay, and I put a coefficient here, then normalization means that the inner product of the state itself, this inner product should be, the modular square of this should be 1. Okay. And if these are orthogonal states, then it requires C1 modulus square plus C2 modulus square plus C3 modulus square to be equal to 1. All right. So for example, C1 could be 1 over under root 3, C2 could be 1 over under root 3, C3 could be 1 over under root 3. All right. Or C1 could be 1 over under root 3, C2 could be say 1 over under root 5, then C3 would be 1 minus 1 over 5 minus 1 over 3 under root. Okay. And I could also have some phase factor with it as well. Okay. So I have to ensure that this thing is satisfied if I have a state of this kind. This is what normalization means. Okay, but if you have a specific question about a specific calculation that is not working out for you, please email that to me.
Doctor, I think she talks about the calculation that we did in the previous lecture. If you can open the previous lecture, please.
Okay, here it is.
Yeah, and scroll up to go when we calculating the probabilities. Yes, sir.
Here?
Yeah. Um, so when we calculate the first one, we get 1 over root 2. But
Mhm.
when we try to calculate it for 0, 1 state, the results also 1 over root 2, but we say that the result will be 0.
Okay, so if I put a 1 here, say 1 here.
Yeah, we did it under this.
0 1. No, but it can't be 0, because then this bra 1, you take the inner product with cat 0, it should give you 0.
Yeah, but when we take the inner product with يعني when
But
we
then, in the second case, after
so
the plus,
plus 1 1,
0 here,
so
and there's a
it's
1 here.
1.
No, but so if this is 1, okay, let me just change this a little bit. I put 1 here.
Yeah.
Now the the inner product of cat 1 with this is 0. Okay. So inner product of this, or let me change the color here. Inner
Nurad,
product of this with this is 0.
Yeah, but plus 1
Yeah,
with
plus,
1, it's 1.
yeah, but of course you have to multiply it with the inner product of this with this. That is 0.
And also it's plus 0 with 0, which is 1.
Yeah, but in there are so let me email this to you after, or put it on the Google Classroom. So there are two terms. In one term, one of the term is 0, and in the other term, the other second qubit term is 0.
Exactly.
So let me put this on the Google Classroom after this class. I will solve this for you.
Okay. Thank you.
Sir, a humble request to upload the video lectures as well. I unfortunately missed the last lecture and I really need to catch up.
Yeah, we just takes a bit of time. Uh, I think after 1 or 2 days, both the lectures for this week will be uploaded. Yeah, but we'll try. Mosina will try to expedite this, inshallah.
Thank you so much. Thank you so much, sir.
All right. So sorry for the flaky internet connection today, but I hope I get things sorted out before next week. So inshallah, we'll see you on next Saturday. Thank you very much, everyone, for holding out and sticking around. I hope this is all going to be useful somehow. Thank you very much, and masalam and Allah Hafiz.